Namaste. Welcome back to Lecture 2. This is Shree from Eduland Foundation. Before we dive into protons, let's take a quick look at what we did in the last lecture. For those who could not attend the first lecture, please go and check the link in the description box. And those who were with me, thank you for joining. In the previous class, we studied that anything which has mass is a matter. We also understood that matter is made up of very tiny particles called as atoms. Where did they get this word from? Most of the words are either derived from Greek or Latin. Similarly, the word atom is derived from the Greek word atomos. Many people in those days, especially the philosophers and the scientists, were working on the atoms. Among them, a famous philosopher by name Kannada from India and a great philosopher by name Democritus believed that matter was made up of atoms and these atoms could be divided to a certain extent. We also studied in our previous class that the word atom was coined by Democritus. We also learned that John Dalton proposed his theory of atom, which stated that atom was the tiny and the fundamental particle of any element which could not be created nor could be divided. When two objects attracted each other, this led to the curiosity among other scientists, and we also observed J.J. Thomson's experiment on discharge tube, which led to the discovery of electrons. Now, let's take a ride into the protons. Let's get started. It was Goldstein, who was J.J. Thomson's student, observed and identified that if there were electrons inside the atom, then the atom could not be stable. But the atom was stable. So this made him think that there was something inside the atom which made it neutrally charged. He just followed his teacher. He conducted the same experiment but with little alterations. He connected a positive metal rod to the positive terminal of the battery and the negative terminal to the negative rod to the negative terminal of the battery and passed a very high voltage of 10,000 volts under the air, which was reduced to 0.01. Now you may be wondering, why are they using metals inside the discharge tube? Did we not understand from our previous lecture that matter is made up of atom? Are our metal rods not atoms? Hence, they took two metal rods inside the discharge tube. So Goldstein, being a student of J.J. Thomson, was not satisfied that there was only electrons inside the atom. He felt that there was something else which made the atom stable. So he conducted the same experiment. He took a discharge tube, placed two metal rods inside it, connected the positive terminal to the metal rod and called it anode, and connected the negative terminal to another metal rod and called it as the cathode. Now he passed the electricity at a very high voltage. He was waiting for some change. Nothing happened. See, these scientists keep working on their experiments for many times. They do not give up. There is something very great to learn from them. So when nothing happened and when the zinc sulfate did not glow, he thought, probably the positive charge is very heavy. So he made holes in the negative rod and called them as perforations. Now he passed the electricity through a very high voltage and he found that the positive charged particles passed through these perforations on the cathode, touched the zinc sulfate and zinc sulfate started glowing. Hooray! There was a great discovery here. So he discovered that the atom had subatomic particles like electrons, which were negatively charged, and positive charged particles called as protons, and hence the atom was neutral. Since the rays passed through these perforations, these are also called as anal ray experiment because the positive charge passed through the pores on the cathode rod. These are also called, this experiment was also called as the anode ray experiment. Clear? Can we move on? Come on. Now, there was discovery of subatomic particles inside the atom. They were electrons which were negatively charged and protons which were positively charged. Everyone wanted to understand how the protons and the neutrons were arranged inside the atom. So it was J.J. Thomson again who jumped in and said, it's very simple. Just consider a plum with a pudding. He said that the pudding, which was a larger mass, was the positive charge, and the plum, which was inside the pudding, was the negative charge. Confused? Don't worry. Let me explain it to you again. Let's look at an example of this watermelon. He said that the red pulp, which is the larger area in the watermelon, was a positive charge, and inside the positive charge was embedded the black seeds, which were the electrons. So his model is called as the plum pudding model. His model of atom was called as the plum pudding model. So he said that the larger mass, that is the positive charge, is present in a large area inside the atom, and the electrons are present only embedded inside the positive charge. However, this did not hold good for long. Later, it was Rutherford who wanted to identify whether the structure of the atom as proposed by J.J. Thomson was right. For this, he took a gold foil which was broken down into very thin sheet. The gold foil was so thin that it had only 1,000 atoms in it. He passed an alpha particle through this gold foil. Now, why did he pass the alpha particle through the gold foil? Because alpha particles were positively charged. You may be wondering, why did he take gold? Did we not understand that every matter is made up of atom? So, gold was also made up of atom, and if we go by J.J. Thomson's model of an atom, the gold foil should have a large positive area, and when the positive rays were hit on this foil, most of the rays should get deflected. Isn't it? Are you with me? For example, when we bring the north pole of a magnet and north pole of another magnet together, the two positives repel, isn't it? So if J.J. Thomson's model of an atom was true, which was positive charge particle were in large area when compared to electrons, in that case, then the rays which were emitted by Rutherford's model should have got deflected. Let me make it clear for you. Now, J.J. Thomson took gold foil which was broken into very thin sheet. It had only 1,000 atoms within it. He took gold foil because gold is easily malleable. It could be broken into thin sheets. Then he took alpha particle emitter which was doubly positive charged. Around this, he covered it with zinc sulfate. We already know from the previous experiments that zinc sulfate glows when the electric charge particles fall on it. Now, Rutherford took doubly charged positive particles and bombarded it on the gold foil. Tug, 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 tug. He expected the rays of the alpha particle to deflect back. But to his surprise, all the rays went straight without deflecting, and only one or two rays deflected, and out of 12,000, only one deflected 80 degrees. This was a great observation what Rutherford made. So this experiment is very famous and it is called as the scattering experiment. If we go by J.J. Thomson's model, the gold foil should be completely positively charged, and when the alpha particle were bombarded on it, all the rays should have deflected back. That didn't happen. So this led to the observation that atom was empty. Only few particles were deflected. So the positive charge in an atom was available only in the center, and it was very, very small. So Rutherford's model of an atom led to the discovery of nucleus inside the atom, and he also explained that the atom was positively charged particle. The atom had positively charged particle only in the center, and around the positive charged particle the electrons were revolving. I hope this experiment is clear to you. If yes, come on, let's move on. So let's repeat this again. So what was Rutherford's observation? So he found that atom did not have positively charged completely filled inside it, but atom had empty space and the positive charge particle was present only in the center. Very few particles were deflected from the path, indicating that positive charge of an atom occupies a very little space. So, from his experiments, he concluded that the radius of the nucleus is 10 to the power of 5 times less than that of the atom. That is, the nucleus is very, very small inside the atom. So, let's look at Rutherford's observation once again. He said that most of the space inside the atom was empty because through the experiment, the alpha particles moved straight through the gold foil and did not deflect. He also said that the alpha particles which went through the gold foil deflected from their path, indicating that positive charge of an atom occupies a very little space. So, unlike J.J. Thomson's model, the atom did not occupy the entire mass of an atom. Just imagine the pulp of a watermelon. This was J.J. Thomson's model. But Rutherford said atoms were not, the positive charge inside the atom was not like the pulp but was present only in the center. And from the data, he also concluded that radius of the nucleus is 10 to the power of 5 times less than that of an atom. Here, let's move on. Okay. This slide depicts how the Rutherford's model of an atom looked like. He said that atom was empty. You can see that there is a lot of empty space in the atom, and the red part inside the atom was the positive charge. It was present in a very small amount, and around this positive charge were the negative charge particles revolving. The size of the nucleus was very small when compared to that of an atom. Here you can see the size of the nucleus is very, very small. So Rutherford's model of an atom looked exactly somewhat very opposite to that of J.J. Thomson's model, where J.J. Thomson's model had the positive So entire atom was made up of positive charge particle in which the negative charge particles were embedded. But in Rutherford's model of an atom, you can see that the positive center was having protons and the positive charge was very, very small, around which the electrons were revolving. Now, we have two models now, but what was the drawback of Rutherford's model of an atom? Now, Rutherford said the positive charge was in the center and these were called as the protons. Revolving around it was electrons, and the electrons were moving in a circular path which was not stable. Now, this you can imagine as, suppose I ask you to go around me, round and round and round and round. Probably you will go around me for 10 rounds, 20 rounds, 30 rounds, and after which you would just sit down and say, "Ma'am, I am tired. I give up." The same thing happened. Rutherford said that the atoms had positive charge and around which the electrons were revolving. He said the electrons were going around the nucleus in a circular motion, and as they went around the circular path, they emitted energy because it was accelerated went, and they lost energy after some time, and all the electrons fell down inside the nucleus. This would have made the atom highly unstable, but the atoms which were around were quite stable. So this theory and this model of Rutherford was not accepted. Let's look at the drawbacks of Rutherford's model once again. He said that the atom had a positive center and the positive charge particles were present in the center and they were very, very small. Around the positive center, around the protons, the electrons were revolving around. And how did they revolve? They revolved in a circular motion. They went round and round and round and round and round. And finally, they became very tired, they lost energy, and they collapsed and fell inside the nucleus. If such was the case, if electrons fell off, lost their energy, how could the atom be stable? It wouldn't have been stable, but the atoms what we had were all stable. So Rutherford's model of an atom had drawbacks and was not accepted. Well, we have come so far in the structure of an atom. Our next lecture would be on Bohr's model of an atom.